So for our last example, I thought we'd go out with a bang. Again, carrying through this idea of needing to potentially mix integration techniques within a problem, use substitution and integration by parts. Let's take a peek at this next one. So we've got the integral of the sine of the ln of 2x dx. Now notice that we don't have a product of two functions of x like we normally had with integration by parts. What we have is we have a composition of a number of functions that we're needing to integrate. So when we're dealing with integrals of composite functions, that tends to lead us to use substitution. So let's try a substitution method to begin here. So if we were to start off with just a good old substitution problem, maybe we'd let u be equal to the ln of 2x, which would yield a du of 1 over 2x times 2 dx, or just 1 over x dx. Okay, so there's our u and our du. Let's see how far that gets us with this problem over here. So now we've got the integral of the sine of u dx. Okay, well this poses a slight problem because we got rid of the x, but we now have this dx. And if we look over at our original statement and said, okay, well how can I get dx out of this? What we would do is we would multiply both sides by x, and we'd have x times du. Alright, so if we now have addressed the du problem, let's put this back in, and that's going to leave us with sine of u times x du, or the integral of x times sine of u du. Alright, so this kind of seems to be a little bit frustrating. We're bouncing back and forth here. Now we got the first x out and the dx out, but in the process, another x popped back in. Now remember, we did some problems in the substitution method section where we were able to deal with this extra x. What we ended up doing is going back to our u statement, and solving that for x. So let's go ahead and solve that u statement for x now. So if we've got u is equal to the ln of 2x, we can get rid of that ln by rewriting this as an exponential. E, the base of the natural log to the power of u, is equal to 2x, which gives us 1/2 e to the u is equal to x. Alright, so now we can go back in and we can finish converting this to a new variable u. So we'll have the integral of, in place of u, we're going to put 1/2 e to the u times the sine of u du. Or, if we pull that 1/2 out, we're going to get e to the u sine of u du. Okay, so good news, bad news is we finally converted this to a function of u. So the question now becomes, well, do we actually know how to integrate this? That's the whole point of substitution, is we change the variable into something that is a function we can integrate. Well, we've actually done this already in this section, and I'm gonna kind of cheat and just use those results. So in this particular problem, now we notice that we need integration by parts. Good news is that we've already done this. So we did this one. If you go back a number of examples in this series, it was the integral of e to the theta sine of theta d theta. So we're just going to use the results from that. So if you go back, I mean, this was actually kind of a tricky integral in of itself. This is the one where we had to do integration by parts twice. Then we had to solve for the original integral because it showed up again. So we're going to just use those results from the previous exercise. And that's going to leave us with 1/2 times, and the results from that example were 1/2 times e to the u sine of u minus e to the u cosine of u. And then, of course, we've got that plus c. So if you want to see how we got that, go back in your notes and check that example to see where that came from. So we've successfully integrated this. The last thing that we need to do is to get this back into our original variable, which was x. So as with any substitution problem, that last step is revert back, plug in your original substitution for u, and then we'll be done. So let's go ahead and finish this out. So noting that u is equal to the ln of 2x from the starting problem. If we multiply those two 1/2s together, we're going to get 1/4 times e to the ln of 2x times the sine of the ln of 2x minus e to the ln of 2x times cosine of the ln of 2x plus c. Also recognize, this is going back to pre-calculus here, you've got e to the ln of 2x. Recall that this is essentially e to the power of the log base e of 2x right here. We're composing the logarithmic exponential, or the log base e with the exponential base e. These are inverses of each other, so they just simplify to 2x. So we're going to go back and we're going to make that simplification. So now we've got 1/4 times just 2x sine ln of 2x minus 2x cosine ln of 2x plus c, and then we could factor that 2x out, and that's just going to leave us with 1/2 x times the sine of the ln of 2x minus the cosine of the ln of 2x plus c. And that's about as good as we're gonna get here. So a number of twists and turns along the way, but it's one of these problems where we get to see a little bit of everything. We've got a u substitution, we have an integration by parts, not a simple one. We also have to utilize some properties from pre-calculus. So kind of a nice problem to wrap up this section on integration by parts.